Production LLM systems should not treat every prompt as brand new. In this module, we'll look at how to reuse safe answers for exact, similar, and simultaneous requests, reducing cost and latency while protecting correctness with thresholds, freshness rules, and tenant isolation. Here's where we are in the larger production path. First, we examined why the original LLM system failed under real-world load. Then we rebuilt the serving foundation for cost, scale, and control. Now we harden that foundation with semantic caching and deduplication, so the system avoids unnecessary inference whenever it safely can. Users rarely repeat the exact same prompt. More often, they repeat the same intent in different words. Semantic caching captures that pattern. When a new request is close enough to a trusted previous request, the system can return the stored answer instead of calling the model again. That saves tokens, lowers latency, and reduces pressure on queues, GPUs, and external APIs. It can also help absorb traffic spikes while scaling catches up. But semantic caching is not just a speed technique. Its thresholds, freshness rules, and safety checks directly affect correctness. Exact caching is the conservative starting point. It says reuse this only when the request key is identical. That makes it useful for deterministic prompts, scheduled jobs, and repeated application-generated calls. Semantic caching goes further by asking whether a new request means the same thing. It can catch paraphrases and similar intent, which improves hit rates in natural conversations. The trade-off is control. Exact caching is simpler and safer. Semantic caching needs thresholds, metadata, and validation, so similar does not become wrong. A key design decision is what actually becomes reusable. The cache key might be the raw query, a cleaned and normalized prompt, or the full prompt plus retrieved context. The cached value can also include more than answer text, such as JSON, tool results, citations, model details, and confidence signals. Attach metadata every time: tenant, model version, prompt version, corpus version, timestamp, and policy scope. Be especially conservative with personal, tenant-specific, or fast-changing information unless access controls and expiration rules are very strict. Semantic lookup begins by turning the request into a stable representation. First, normalize away noise like formatting, casing, and accidental wording changes, while preserving the context that affects the answer. Then generate an embedding for the right unit of reuse: the user query, the full prompt, or the prompt plus retrieved context. A vector index finds nearby cached embeddings quickly, often with approximate nearest neighbor search. Those candidates are not reused automatically. They still need to pass similarity thresholds and metadata filters before the cached response is treated as a hit. The cache key needs to include every input that can materially change the answer. Caching only the user query gives strong reuse, which can work for stable FAQ-style responses, but it may ignore instructions, permissions, or fresh evidence. Prompt-level caching is a safer middle ground because it includes system and developer context. For RAG, personalization or tool workflows include retrieved documents and other relevant context as well. The more specific the key, the lower the hit rate, but the lower the risk of serving the wrong answer. Similarity thresholds are the gatekeeper. Set the threshold too low, and the system reuses more answers, improving cost and latency. But it may also treat meaningfully different questions as close enough, creating a false positive, a confident cached response that is wrong for the new request. Set it too high and accuracy improves, but many reusable answers are missed. There is no universal setting. Tune thresholds with labeled examples and production traffic, then adjust by risk. Legal, medical, financial, and customer-specific tasks usually need stricter thresholds than low-risk informational queries. A semantic cache hit is only a signal, not automatic permission to reuse the answer. Production systems usually pass that hit through several gates. Metadata must match, including tenant, model, and prompt versions, language, region, and policy scope. The candidate must also meet the similarity threshold, and high-risk cases may need a re-ranker or equivalence check to confirm the meaning is truly the same. Finally, the cached response still has to fit the expected schema, tool contract, and safety rules. If any gate is uncertain, generate fresh. Reuse must also respect the original authorization boundary. A request should not simply ask, "Have we seen something similar?" It must first know who is asking, which tenant they belong to, what role they have, and which region or workspace applies. That context should route the lookup into the right namespace, filtered partition, or separate index. Global caches are appropriate only for public, non-personalized content. Every reuse decision should be logged so compliance teams can prove why a response was served and investigate quickly if isolation fails. An LLM cache is trustworthy only while its assumptions remain true. Time to live handles obvious aging, especially for prices, policies, or fast-changing facts. But time alone is not enough. Each cached answer should carry the corpus version, prompt version, model version, and retrieval settings that produced it. When documents, embeddings, safety rules, or response formats change, matching entries should become stale or invalid. The practical rule is simple. If a wrong cached answer would cost more than regenerating it, invalidate conservatively and refresh from the current system state. Caching handles previous work. Deduplication handles identical work arriving at the same time. Instead of letting every matching request enter the GPU queue, create a deduplication key from normalized input, tenant, prompt version, model route, and any context that changes the answer. The first matching request becomes the leader and runs inference. Later matches become followers and wait on that result, with a short in-flight TTL so locks cannot live forever. When inference finishes, the single result is returned to every caller. This is especially valuable for spikes, retries, polling loops, and double submits. Together, these techniques form a layered decision path. Start with exact cache because it is fastest and safest for repeated deterministic inputs. If that misses, try semantic cache, but only return a result after similarity checks and validation. Confirm the intent is equivalent. If both caches miss, deduplicate in-flight requests, so 10 identical misses wait on one generation instead of launching 10 model calls. Only then generate with the LLM. The new answer can update the exact cache, the semantic cache, or both, improving future latency and cost. Once caching is in production, keep measuring it. Track whether it is actually reducing latency, tokens, and cost while watching for false positives and stale answers. Pair operational metrics with quality signals such as feedback, escalations, corrections, and offline evaluations. Segment the data by tenant, root, prompt type, model, language, and risk level, because averages can hide failures. The safest tuning pattern is gradual. Shadow first, canary with thresholds, and require human review for high-risk domains. Good observability turns caching from a guess into a controlled production system. The core lesson is straightforward. Reuse LLM work, but never blindly. Semantic caching helps when requests are meaningfully similar, and deduplication stops concurrent repeats from wasting capacity. Production safety comes from conservative thresholds, metadata checks, freshness rules, tenant isolation, and strong observability. Next, we extend this reliability toolkit with circuit breakers, fallback paths, retries, load shedding, and GPU-safe concurrency.